INSPEM HPC is all about briefly. So basically this is the diagram that shows you how this cluster thing actually works. Okay. So if this is your machine, okay, it can be from any OS, it can be from Windows, Linux or Mac, okay. And then we use this secure shell, which is known as SSH, okay, to establish a connection to the head node of the cluster. Okay. The head node is also known as the login node, and while you are executing any task, it is known as the master node. Okay. And from the master node, okay, you actually send it to the compute nodes. So in INSPEM we have got 8 compute nodes. These compute nodes are also known as worker nodes or as slaves. Okay, slave to this master. Okay, so we will actually execute our computations in the compute nodes. The head node is only used for login and logout purpose, right? So whichever file, whatever files that you actually insert to the head node will be automatically available in the compute nodes, because we have got this network file sharing system in Linux, right? So you don't have to worry whether your files are in the compute nodes or not, right? So in each compute node we have got 12 cores. Okay, cores here means the processors basically, right? So if you look at the total number of processors, it would be 12 times 8. So we have got 96 processors in total, right? So this is the one I've given here. Okay, we have got 8 nodes and 12 processor per node. PPN stands for processor per node, right? A node is not a processor. A node is a host. Okay, it is just like a computer, another computer, right? Okay, but in this terminology we call it server. Okay, so a node is a host which contains 12 cores, right? So for introduction, okay, yeah. So before that, you should log in. If you look at your handout, you have your username, right? Okay, SAWONA and number, and the password is a common password. Okay, it is SAWONA 2016. Remember, when you type your password in Putty, it is not going to be visible. Okay, so don't worry. Just type and press enter. Okay, and then what you can do is, so I'm going to log in as SAWONA 1. Okay, type my password SAWONA 2016. Okay, so this is what all of you are going to get. Okay, everyone got it? Okay, so CE here, okay, is the host name of the head node. Okay, CE stands for computing element. Yes. Okay, if you go to Putty, you go to session. Okay, in the host name you have to type this IP address. Yes. 172.16.241.116. Host name, yes. It's host name or IP address. Yes. Open. Okay. So there will be a message asking you the server's host key. Just press yes. Okay. Just press yes, and then log in. Okay. Kena ada wifi. EMS INSPEM. EMS INSPEM. EMS INSPEM. Password University Putra Malaysia. Semua small letter dan space. P-U-T-T-Y, okay? Not with SCP, yeah? Okay, so everyone got this? Right? Okay. So, okay, this is a Linux operating system. So you need to know very few Linux basic commands. Okay? So for instance, if you want to see, you're already in your home directory now. Okay? If you want to see what is the contents of your directory, you just type ls, which would list down all the contents of your directory. Okay? So you should have about few files here. Okay? But you're not going to use all of them. Okay? Yes. No, don't use this file. Not this file. P-U-T-T-Y. Not this file. That will use. There we go. Yeah. No, not SAWONA. Username, please use your own username. Don't use SAWONA 1. Right. Type your password. Okay. Just type. It's not going to appear there. No, it won't appear. Your password is not going to appear. Just type and press enter. Okay? Press enter. Right. So if you look at the handout, okay, maybe we'll just do the first one, okay, and then we move to Dr. Asila's session, okay. So what you need to do is, okay, how to change, okay, if you can see this is in a different color, okay, because this is also a directory, it's a subdirectory here, okay. So how to go into this directory is simple, okay, you just type cd and the name of that directory, okay. So you are in, so if you see, you are now inside the intro directory, right? And then again, to view your files, just type ls, okay? So you have a few files here. So we are just going to use the first example here, task 1, okay? First thing what we are going to do is, okay, how to view a file is, you can use the command cat, C-A-T, okay? And then you can type the name of the file, task1.c, and enter, okay? So this is task1.c, right? Got it? Okay. So now what we are going to do is, we are going to compile this. So we are going to use the command npicc. Okay? npicc is just a wrapper for GCC, the GNU C compiler, just like your Visual Studio and stuff. Okay? So npicc, and then the name of your C source file, task1.c. And then -o, okay? Next is the name of your object. Just name it as the same name, but without the .c. Without .c. and press enter. Okay, you can see FAICC task1.c -o and then task1 again, but without the .c. So we have actually compiled this task1.c. So now if you view your directory ls, you see there is this compiled C file here, task1, okay, which you never had before this, right? This is already compiled. So now we are going to execute this file, okay? So the usual way to execute is this, okay? Dot backslash and then the name of your object, task1. Let's press enter. So this is the output. So here we are only using one processor, okay? So this is a sequential thing. Next, we are going to use NPI-run, okay, which is meant for parallel processing. Okay, here when you have NPI-run task1, okay, what happens is if you enter, you are still going to get the same because we are running it with one processor. Okay, so the next slide, if you look at the handout, okay, okay, we have added NPI-run -np. NP stands for number of processors. So I just put it as 4 here, okay, and then you enter. Okay, so you see now we have got 4 instead of 1. So this is the difference, right? Okay, so since getting time, okay, CD again, everyone. Once you have got this, type CD. Okay, you are going to go back to your home directory, which has this tilde symbol. Okay, and then if you look at your handout, the first line here, okay, everyone please type this. Okay, what you have to type is you have to type QSUB QSUB dash capital I dash small letter L. It's not 1, it's L. Okay, and then type the name of the compute node that is given to you. This one is given in your handout. QSUB-I-L, CD first, okay, and then nodes equals to whichever compute name is given here, okay. Nodes equals to the one. Yes, this one. Okay, CD and then yes. Dah boleh. Dash I dash L. Semua dah masuk kan? Okey. Ada orang?
Dia tekan LS, nanti dia akan listkan balik simpan, dan dia tambah PASK
Notes equals to
PASK 1, tak ada kat sini. So, yang tu, yang dot slash class 1. Kita nak run.
dah.
Lepas nanti I run, dapat compiling.
Okey, yang example tadi kalau tak dapat buat tak apa. Lepas ni Dr. Asila pun akan gunakan example tadi. Sekarang yang penting ni tolong masuk ke compute node. Okey? This one, this first line. Okey? Q sub dash I dash L and then the name of the compute node. Okey. Okey, kalau dah masuk. Okey, once you have entered the compute node, it will show your name and compute X. Okay? Whichever number you have. Alright? Tak apa? Tapi CD dulu. Okay. Sekarang type tu.
So I will wait until everybody ready.
Ready? Okay?
Everybody ready.
Okay. Okay. Dah masuk compute tak? Okay? Make sure it is at compute. Alright. Okay. Okay, but now now it is like, yes, the first line. Dash I dash L and then it's okay, sini dah okay? Sini dah okay? Dah okay? Okay? Dah okay? Ya. Guna itu. Dah okay? Alright. Semua okay? Dah masuk Okay, berapa? Okay, 8.
Underscore dash was the letter of I and then space dash R. Pusat space dash capital letter of I space dash N. Ada dia.
Okay. Now, this time. Okay. Okay, anytime. You sum space. Okay, dash I dash L. No space without this. Dash I. Okay, space first.
Kan tadi kan yang pusat tu kan.
Dash L. Then you type notes equals to this one. Okay. Copy 3. Need of gauge. Dah. Cute. Tapi tekan. Minus L. No, I see it's more than Semudah eh? Okay. So once you're in the directory, you can type ls to see all your files are there. The files that you saw in the CE just now. Okay. Everybody's in copy note, huh? Okay.
So, can I start? Yes, Assalamualaikum and good afternoon. So, go back to where we left just now. Okay, so I believe we stop at here, right? So I believe we stop at here. And maybe, sorry, so maybe you can look at your source code. You can look at your directory right now. Okay, everybody look at your directory and then try to compile MPI CC dash. So now we are trying to look into the sequential hello world. Okay. Hello underscore seq.c. Okay, so you have to do hello underscore seq.c.
GCC. GCC.
So what we're going to do right now is that we are compiling on using C, not MPI yet. So GCC hello underscore sequential.c dash go hello underscore sequence. Okay. So this is going to be the object name or the executable name. Okay. So how to execute? You just press dot backslash hello underscore.
Okay, kalau mana nak tap?
So you can see here.
Tap.
So that is the result. Process 0 on 1. Okay, process 1 on 0. Okay, because the compute node is actually right now is using the 0. Okay. Everybody okay? Okay, so right now. Next is we are trying to compile using MPICC dash go hello underscore PAR and hello underscore PAR.c. So if you success, you can see there is the green color hello world over here. Okay, and hello underscore PAR. No. Okay, so this is the command. This is the command. Instead of GCC, now you have to change to MPI CC. Okay, to compile in MPI environment. Okay, next, if everybody has done that, now we want to execute MPI run, MPI run dash NP 2. So I request for 2 processor dot backslash hello underscore PAR. Okay. So you can see process 1 on compute 1 out of 2, process 0 on compute 1 out of 2. That is the output because I request for 2 processors. So you can see 0 and 1. Okay. So everybody got that this result? Okay. Not yet. Okay. If not yet, maybe you can put up your hand so that you can help. Right? Okay.
Avoid spelling mistakes, typo. Okay? Your file names always wrongly typed. Yes? MPI not then no need to retype. Yes. Use up arrow and then you have
Okay. So if everybody have got that result, I would like to go back to this slide because I want to explain what is happening actually. Okay. Yes.
Hello in the future. That's what I'm seeing. Everything is fine. Hello, you have to recompile that. Okay. That's it. Then we use API right.
Numprop is the total or the size, the MPI from size. Okay? So if we have 2, process 0 on compute 1 out of 2. Process 1 on compute 1 out of 2. Okay? So I will show the this command MPI run -np2./elopa. So this value will go to com size. Okay, com size, whatever variable that we declare in that com size will hold this value. Okay, and that com rank will label. If 2 means it will label 0 and 1. So we can see the output. Okay. Process 0 on compute 1 out of 2 means this is the rank, this is the number and name of that server, out of 2 is the total where we request from com size. Okay. So let's say we request more than that. Okay, now you can see process 0 on compute 1 out of 4 and so on. So this is the rank, this is the total size of processes that we request. Okay. So everybody understand? The first program just to show you how we going to grab or get the value of total of processes and label all the processes with the rank 0, 1, 2, 3. Remember, the rank will start with 0. If you start from 0 until 3. Okay?
Because VI is
Okay, next. I will go back to this slide. Okay, so I want everybody to listen carefully because this explanation will explain each in detail what happened when we execute that file. So in a nutshell, this program set up a communication group, as I mentioned this morning, a communication group of processes where each process gets its rank, prints it, and exits. It means each processor in this communication group where we mentioned about the MPI forward will get its rank, print, and exit. Okay. So it is important for you to understand that in MPI, this program will start simultaneously on all machines. Okay. For example, if we had 10 machines that running this program, it means that 10 separate instances of this program will start running together on 10 different machines. This will be assumed like when we request 2, there's 2 PC running at the same time. Similarly, that's right. Okay. This is a fundamental different from ordinary C program where once someone can run the program, it was assumed that there was only one instance of the program running. Okay, now we go line by line. Input as standard input output, this is the C command program. And then MPI.h, include MPI.h, include the MPI function. So you must have this. The file MPI.h contains prototype for all the MPI routines in this program. This file located here if you want to have a look. Okay. Then next is the main integer argument C and argument B. So the program starts with the main line which takes the usual 2 arguments C and argument B. So when we use the MPI run, that argument will send with this variable. Okay. And the program declares one integer variable known and size. Okay, the first step of the program, MPI init. So inside here you can see the same as in main, argument C and argument B. Calls MPI init to initialize the MPI environment. So when the program reads MPI init, it means it will understand we have to initialize this to MPI environment. Okay, and generally set up everything. So this should be the first command executed in all programs. So this routine takes pointers to argument C and will look at them, pull out the purely MPI relevant things, and generally fix them so you can use command line argument as normal. So you have to have the MPI init. Okay, com size. Return the total number of MPI processes in the specified communicator such as MPI convert. So remember, this you cannot left out. Okay, remember, this MPI convert as what we call as a communicator. So it will indicate, okay, this process that we request just now, MPI run-NP2, is a group for this program. And the variable that holds that number of 2 or 4 that we request is size. So you can change that variable, anything that you like. Okay, next is MPI conrank. MPI conrank, as I mentioned just now, MPI conrank will set node to the rank of the machine on which the program is running. Remember that in reality, several instances of this program start out on several different machines when this program is run. So these processors will each receive a unique number from MPI conrank. Okay, so because the program is running on multiple machines, each will execute not only all of the commands for explain, but also the hello message printf, which include their own rank. Okay, so if you notice that all the processes that you request print their own printf, right? Okay, so we can read here. If the program is run on 10 computers, printf is called 10 times on 10 different machines simultaneously. So that's what happens. Okay. Just now I mentioned that 10, if you request 10, means that 10 processors looking at the same program. Okay. So the order in which each process executes the message is undetermined, means based on when they each reach that point in their executions of the program and how they travel on the network. Okay, so the 10 message will get down to your screen in some undetermined order. So that's why you notice it's not indeterminate order, 0, 1, 2, 3, it's undetermined based on who comes first, who reach first. Okay, do you have any question? So again, this program is actually would like to introduce you how you track the number of processors, how you label the rank, and how you need to understand that all programs will see the same program at the same time. Okay, that understanding is very important. Okay, I will let you know why it is important. Okay, so lastly is MPI analyze. Okay, so if everybody understand, we can go to the next program, which is send and receive. Okay, so that first example is not, we are not using any communication. You realize we just call com-size, com-rank. We don't communicate, we just display. Okay, but now I'm going to show you how we're going to communicate between process 0 and process 1. And this communication is actually what we call as a ping and pong. 0 sent to 1 and 1 sent to 0. Okay? Okay, so if you look at this program, so this one is normal, so you have to have com-size, com-rank now. The variable is num-size for size and rank for com-rank. Okay? Next. So if rank 0, destination equal to 1, source equal to 1, MPI send, MPI receive. Else if rank equal to 1, destination 0, source equal to 0. So what is this actually? Okay, so I'll try to explain. So in this part, if rank equal to 0, so who's going to read this? Only processor 0, right? Processor 1 will not read this because we put if rank equal to 0. And then if we read destination is 1, source is 1. Okay. So inside this bracket, our message, if you identify our message is X just now, right? Okay. The out message is this one. The out message is X. Okay. And then the value, the value, the value, the size of the message is 1, and then the curly MPI char is character. Okay? And then remember, we have to put the destination. Okay, the destination is 1. Now this send will send X to processor 1. And then tag to make sure there is a tag there and MPI convert. So what happened here? Okay, process 0, process 1. Okay, so MPI send the destination is 1. Okay, then it will send here. Okay. So when we execute MPI send means the X will travel to 1. To make 1 receive this X, it needs to run the MPI receive. So MPI receive, everything is the same. In message is also X, means that that is the message that is going to receive. MPI char is everything is the same, and then the only difference is the source. Source is 0. Okay? So the source is 0. So then it will receive the X here. Okay, so now what happened here is only ping. 0 send to 1. So MPI send from 0, MPI receive from 1 to receive the command. Okay. So now next is processor 1 would like to send the message to 0. So that's why you see there is MPI send over here. MPI send the out message of MPI char, now the destination. So the destination now is 0. Okay? So it's going to send the message. So now the destination is 0. So it needs to call the MPI send. Then again, to receive that message from processor 1, processor 0 needs to call MPI receive. And the source is from 1. Okay? Then it completes the form, string and form. This is what we call as a point-to-point communication. Okay? So what you have to remember is how to arrange inside this bracket. That's all. Okay? You understand? So maybe this time you need to try. You can try to compile and execute this program. The name of this program is send. You can do in your directory. Type ls. You can see there is a send.c. Okay. Do the same. mpicc -o send and then space send.c. Enter. Okay. mpicc to compile. Remember we need to compile first. -o send the object name send.c. Okay. This is how you should compile. mpicc-o send.c. -o is to name your output or execute file. That's why there is no .c. Send.c is to call the send.c. Okay? So for this program, we actually need to request only 2 processors because we just do an exchange data from 2 process. So you can execute. So you can see the result. Okay. Task 0 receive 1 char from task 1 with tag 1. Task 1 receive 1 char from task 0 with tag 1. Okay. So this is where we apply the concept of send and receive. So So, any question? It's okay if you don't really understand 100%. That's what is one job, and yes, because it's easy from yes, look at your program. Okay. So this is how we make the printf. This is how we make the printf. Okay, look at the printf. Thus, and then it called the rank. It's called the rank, count, MPI source, MPI set. Okay, so that's rank. So whatever rank is there, that's why class 0 is from processor 0, class 1 is from processor 1. Okay, receive one child from class, again the rank, and then and the source with that one. Okay. Okay, do you understand? Any questions? So maybe so this one, this example is actually the example for point-to-point communication. As I mentioned just now, we are doing the ping and form. So the important thing that you have to understand is to send a message, you have to call MPI send. Okay, and then to receive the message, the receiver need to call MPI receive. Let's say processor 1 didn't call MPI receive, that message will not be received. Okay, similarly to this one. Okay, right now, next is the example of, just now what we do is ping and form. So now I want to show the example, we just do ping. We don't do form. Okay, we just send, for example, like 0 send 31, that's all. Okay, then maybe you can understand more. So this program, if you can look at your handout, the title of the program is greetings.c. Okay? Greetings.c. As you can see, all the same. We have to include API.ph and so on. Okay? Right now, we are using API rank and source again. Okay, you can see that. API from rank. The rank is my rank, the variable. The size is p. Okay. Okay, right. Okay, now. Not 0. Look at the int. If my rank is not 0, so who can read this line? All other processors except 0, right? So if we request 2, 1 will read this. If we request 4, 1, 2, 3 will read this. Okay. So when we execute, let's say that my rank is 1. Okay. So it will read as printf message greeting from process. So let's say now my rank is 1, greeting from process 1. And then we can see that destination is 0. So this is a common C program. As printf means it will not display, it will hold that message in message variable. Okay, so this is a C program. Now this is the MPI program. MPI send message. This one. This is what we're going to send. We're going to send greetings from process 1. Okay. So the length of the message is we're using the string length to measure the size of the length of the message. And then the type is MPI child. And then what is the destination? The destination is equal to 0. So what it means? Process now just now I said if my rank is 1. If the rank is 1 right now, means that processor 1 will send this message to processor 0. Okay? Destination is 0. Check MPI forward. Okay? So let's say now, just now is processor 1 looking at this code. Next is processor 3. So processor 3 is also true for my rank is not 0, right? So it will do the same. It will read, oh, I have to keep message variable as greeting from process 3. Oh, now I have to send the message greeting from process 3 to my destination. The destination is 0. So that will be true for process 1, 2, and 3 if I request NP as 4. Okay? Next. So the code now is else. So if else means that whatever not 1 to 3 is actually 0. Okay? Only process 0 can read this command. Okay, so process 0 will read for source equal to 1, source smaller than B, source plus plus. So what is source? What is source actually? So if we look at this, source, what is source? Integer source, rank of standard. Okay. Source equal to 1, source smaller than B, source plus plus. And then, so let's say right now, source equal to 1, source smaller than 3, right? Smaller than 3, source plus plus. What is our P? So let's say I have to request for NP equal to 4. So what is our P? Our P will be 4, right? Okay, so our P will be 4. Okay, so next, MPI receive message 100, the line is designated as 100, MPI char and source. So what's going to happen here? MPI receive, so message, and blah blah blah, and SOURCE, source. So this source, because this is actually a loop, right? So it will start with 1. So it will start with 1, 2, and 3. So when it reaches 4, it will exit the loop, right? So when it will exit the loop, and then you can see there is a printf. So every time it print NPI receive, it will do the display as printf. There's the printf. There's message. So when the source is 1, there's greeting from process 1. So if the my rank is 2, greeting from process 2, and then greeting from process 3. Okay. So why don't you try to execute your code right now? So what it looks like? So you can use NPI run. Again, if you don't compile, you have to compile NPICC, -o GREEDINGS, and then GREEDINGS.c. So you have to compile. So once you have done compile, you can start run your program. Okay? So you can see here, I'm using 2 processors. So there's greetings from process 1. So what is missing? We replace 0. So why we don't have 0 here?
The loop.
Because just now we do the else, right? So 0, who's actually doing the printf here?
0.
0. Yeah, that's very good. Because else, source is smaller than P. So right now our P is 2, then it will loop only one time. Okay, so it will receive at the same time, after that it will display. Because there is a printf after MPI receive. Okay, okay, so I'll try to use more than 2. Okay, so right now you can see that reading from 1 to 3. So what this program different with the previous program is, first we are just doing ping. Means process 1, 2, 3, send a message to process 0, right? Because the destination, remember MPI send, destination is 0. And what process 0 did, it using the loop, because it needs to receive many messages from all other processes. So it using a loop to use that source. Okay, so source 1, source 2, source 3, and stop until it's smaller than P. Okay. So do you notice that the important here is actually to get the value of com size, to get the level of com rank, and then you just play around with the code. Just now, if else process is not 0, and then else if process 0, then it can read. So the rest is actually the line of code, so only com size, com rank, and then the rest is your C program, and then MPI send and MPI receive. So that send and receive is for communication. Okay. So the important that I want you to understand right now, so we have loop for 3 programs. The first one, you need to understand how to capture the size and rank. And you need to understand that whatever number we request, if we don't control using else, if else, all processors will look at the same program. All 10 processors will look at the same program. So the second program, where we are using the ping and form, so we are using if process equal to 0, then you send. If process equal to 1, then you receive. Okay, so you control using your C program how to read which processor. Because that is the importance of MPI com rank. That label of processor is very important for you to control how the communication will happen. Okay, and then just now we just did for ping. So you can see that although process 0, it doesn't mean that you cannot receive from many other processes. You can, as long as you know how to play around with the loop and that number of processes. Okay, so this is what we call as point-to-point communication. Maybe some of the code, maybe I think this morning or yesterday, Rosanaria showed you how it's using the code. This is sometimes you need to pass the message to a specific processor once you've done your calculation. Okay. Okay, for these 3 programs, I didn't show you how to distribute the load yet. What I just show you how to capture the size and rank and how to communicate using send and receive. So next, I want to show you how you can distribute the load. Okay, so I call this program as data partitioning. So the example of this program is very simple. We have millions of loops. Okay, we have millions of loops, and we want to distribute the loops into several number of processes. Okay. So you can see double MPI underscore W time is how you can use this MPI W time to record the time. Okay. So as usual, we have the init, com size, and com rank. And then I initialize the value of A as 0 and B as 1. And then this is how you want to use MPIW time. So you can record the time, the start time. Okay? And then T1 will hold the value of start time. Okay. I make say that my loop, okay, because I want to do a loop. So that loop is actually 100 million times. Okay. So what I did is I take the size is actually again the total number of processes. So I divide 100 x equal to 100 million divided by size, and then to make sure that all node is under the value of size. Actually, if you don't want this, it's okay. But this thing, for I equal to 0, I smaller than x, I plus plus. So my equation is very simple, A equal to A plus B, because I want to show you how that loop will be increased. Okay? So right now, if we have 100 million, if we are using one processor, 100 million will be looped by one processor. Okay? So if we have two processors, 100 million divided by 2, each processor will have 50 million. Okay? If we have more, then it will degrade. Okay. So if you want to see the result, maybe you can try to compile your program. Okay. So the name of that program is data partitioning. Do the same, MPICC, okay, /-o data partitioning, and then data partitioning.c. Everybody got it? So try to run using one processor. Try to run using one processor. Okay, everybody done? Okay. So now you can see node 0 equal to A is 100 million, because just now I make A is equal to A plus B. And then you notice that the NPI that the time is 3.0268 seconds. Okay? So right now, instead of 1, I want to use 2. Okay. So now I'm using 2 processors. You can see that the time is half from one processor, okay, and the value of A is 50 million instead of 100. Means it looked 50 million times instead of 100 times. Okay. So this is how we distribute the load. If our load is actually the fifth amount number of loops. Okay, now I'm using 4 processors. You can see that, again, this is not in order. You already know about that, whoever comes first with these papers. But the value of A is decreasing to 25 million. And then the W type is now 0.7. This is how you decrease the load using number of processors. Okay? And the time will be decreased too. Okay, everybody understand? Okay, do you have any question? So are you on track? Okay. So I want to ask you one question. For this program, do we have any communication? For this program, you can look at the source code. Do we have any communication between the processes? No, right? I didn't get yes. Okay. So this is very important because I want you to understand. Once we start to declare different identification size, and then we call from rank. So we are in API environment. Okay? So the compiler, then when you execute environment, so it works. Okay? So if your program is kind of like embarrassingly parallel, where it doesn't really need any complication, okay? So you can use the variable of size and load to distribute the load. So this is what I'm trying to make you understand. That once the important is you have the size and rank, then you use the size and rank to distribute the load. Because remember, all processors will see the same program, right? So when we request for processor 0, when it's 0, I don't have to do 100 million because X 100 million divided by size. So you will do this one, I just have to do the 25 million. Next processor 1 did the same, I just have to do the 25 million. Next processor 2 look at the same. So this is the concept why I said you have to understand that all processors looking at the same program. If you don't control that program using if else or loop or whatever that you can control. So if you don't control that, all processors will look at the same program and will do whatever the equation that you decide. Okay, so this program only distributes the load to all the processors that you request. Okay, so let's say right now you want to do a communication. For example, okay, all the processors are done, then you want to broadcast. Okay, you want to broadcast one data from one processor to all other processors. Okay, so remember,
Dr. Asila, maybe you just mentioned why you have the close timing before the printf. The program, you have the T2 there.
oh T2.
Before the printf.
Oh, yeah.
Remember you said that.
Okay, so this
What?
is. So you want me to explain?
And just now you maybe can relate. You say that make sure there's no printf when you parallel.
Okay.
Yes.
So yes, don't put any printf here. So because this is where you need to understand. This is the part where you want to reduce the time. Okay. So this is where you don't put anything silly where you want to reduce the time. So I put the STIW time before the printf because I don't want to record the printf activity. I just want to record what is the activity before loop and after loop. Okay. So you can see the time. This is how I get the time. T2 minus T1. Okay. Okay, next program is actually similar to what we did just now. Okay, what we have done just now. But the only difference is I would like to broadcast the data. Okay. So in the year one, I mentioned that we have two sets of communication, point to point. So we are looking into point to point. And right now, I want to give some examples for collective. Okay. So I'm going to start. Collective involve data sharing between more than two tasks, which are often specified as being members in a common group. It means that in an platform word. So I'm going to start with broadcast. So broadcast means you have one data, you want to broadcast to everybody the same data. Okay. For scatter, you can look at the colors. So you scatter not the same data, but each of one get a different data. Look at the arrows. Okay. So gather is opposite. So once you scatter, you need to gather back the data. For example, you scatter a column of array. Each column goes to process 1. Next column goes to process 2, and so on. So you ask that each of that process need to calculate average. And from that process, you need to gather back of the value of average. Okay. So you can use gather. Look at the arrow. Gather will get back all the data and gather to one process only. Okay. For reduce, it's actually the same as gather, but the extra is it will sum up the value and give the value at the process that requests the value. This is what we call as MPI reuse. Okay? Okay, we start with MPI broadcast. The same as MPI send, you have to understand inside the bracket. What is the point inside that bracket you need to fill in. Okay? So normally it's almost the same. Message, the first one is what data that you want to broadcast. Count is the length of the message. MPI integer is the type of that message, integer, character, char or whatever. Source, from which processor that you want to broadcast the data. So normally we are using processor 0 or 1 normally. Okay? So you can look. Buffer is actually referring to this one. Okay? Starting address of buffer, count number of entry in the buffer, data type of buffer, root, rank of broadcast root. Okay? COM is communicator. So now task 1 will broadcast value of 7 to all other tasks. If you are looking at this picture. Okay? So you can look at this code. Okay, you can compile broadcast.c. Okay, MPICC broadcast.c-o broadcast. Okay, so if you already done the compile, so you can run. So why don't we try use 2 processor? Okay. Okay, so I'm trying to show the difference. So I am not 0 and A is 600,000. No, 60 million. Oh, how many is that? Okay, whatever. So before broadcast, I am not 1 and A is 0. So this is what happened before broadcast. I am not 1 and A is 0. Okay? So after broadcast, note that A is equal to B. Okay? So note 0, B is the same value as this one. And MPI time is this. So after broadcast, note that A is equal to B. So note 1, B is 600 million. Okay? So means after broadcast, then the value of A is actually distributed to node 1. Okay? So you can use more than 2, then you can see the difference. My screen is the font is quite big, so I can see. So you can see from your screen, if you request 4 before broadcast, node 1, 2, 3, the value of A is 0. Then after broadcast, the value of A is actually already in processor 1, 2, 3 memory. Okay. So how to do that? So this is actually similar to what we did just now. Okay. So you can look at the code. I'm trying to make this code smaller. Okay, so we have the COMSAT and COMRANK. Okay. And then this is similar, right, to the one that we have just now. The previous code is almost similar. Okay. Because I divide the loop to the sides. But I don't do A plus A equal to A plus B. But I just make B equal to A. Okay? Then after broadcast, I try to print back what is the value of A equal to B. So B should be the same as whatever before here. Okay? So this is the only command that make the broadcast happen. Broadcast A, MPI underscore broadcast A is a value of 20,000 times 30,000. And then this is the length, MPI integer, the source is 0. Means the process 0 will distribute the value of A to all other processes. And MPI forward. Okay? So I want you to notice something. So look at the code. If not equal to 0, A equal to 20,000 times 50,000, printf I am not 0 and A is 60 million. This is 1,000. Okay. Else printf 64 broadcast. So that's why it shows I am not 1 to 3 and A is 0. So it doesn't get anything. Okay. So only node 0 can read this, right? Only node 0 can read that. And the rest of other nodes will read this. Okay? But all of the nodes can view MPI because all nodes, all processors can view MPI because. So all of the processors 0, 1 to 3 will read. So if processor 0, oh, I need to distribute A to all other processors. Oh, now my rank is 1. Oh, so I'm going to receive a message from 0. So then my rank is 2. Oh, I'm going to receive a message from root 0. That is how the broadcast works. Then the important is you need to realize that look at the source code that the MPI because is out of the if statement. It's not included in the if statement. Means that all processors can see the MPI underscore because. Okay. So how many lines? The MPI lines in this code. So if you look at this code, it's only include these 3 lines and then this line. Okay, MPI double time to record the time and MPI finalize. That's it. So the rest is you need to understand your program and know how or where you should put the MPI because and how to use the size and rank to distribute the load. So here, do we have communication in this program? Do we have communication in this program? Yes. The communication is MPI because where root 0 will broadcast all data to the other processes. Okay, so if you don't understand, I will go slow. So do you have any other questions? Do you have any questions? Yes?
Beza dia dengan set dia.
Dia broadcast yang banyak. So your friend asked, what is the difference between set? So this broadcast, remember we say we have point to point and collective. So the difference between point to point and collective means one to many or many to one or many to many. So now broadcast state is one to many. Yes, so we don't have to do one by one, send to 0. Just now when we did for greetings, we have to do the loops, right? To go for one source, another source, another source, another source. But right now we use the because root 0, process 0 can distribute one message to all other processes using just one line of MPI underscore because. Okay? Okay. Next, I want to show you one more example using MPI reduce. MPI reduce, as I mentioned, is similar to MPI gather, where it will gather the value from processes to one source. Okay, but the advantage of MPI reduce is actually it will sum up if you are using MPI underscore sum. So you will get the value of 10. So the first thing is send bar is address of send buffer, what you understand, and then receive bar is the address of receive buffer. Count is the number of elements in instant buffer. Data type is the data type. So we are using the integer. Operation, reduce operation. So there are few operations. Right now we are using the MPI underscore sum. Okay. Destination. So destination is from where this command comes from. So down the destination is 1. Okay. It's task 1. MPI convert. So the destination together all the results is at task 1 or processor 1. Okay. So now I'm showing you the code. All again the same. So the size is holding by size and note for the rank. And then I start the MPIW time. E equal to 0, B equal to 1. So this equation is similar to the data partitioning program. Okay. So we divide 100,000 divided by size. So if not smaller than size, then it will loop. Okay. It will look for how many value of x. Okay? And then what this MPI reduce will do. So MPI reduce will get the value of A, this value A. Okay? And then we'll put, this is the buffer for receive sum. And then start this MPI integer, and we are going to do the MPI sum, which is the class for all the value. And then I'm not using the 1, but I'm using destination is 0. Okay, MPI convert. So that is the only MPI code. So the rest is just a C code where I want to show what is happening when we do the printf. So if node is 0, so it will print out the total processes and the MPIW time, else the other node will show the value. Okay? So this is the output. So you can see MPI run -np4./time reduce. Node 1 A is 25,000, so it's not 100,000, but it's 25,000 because remember I divide 100,000 divided by size. So now my request is 4. 100,000 divided by 4, we will get 25,000. So this is the time. Okay, and then if you notice, total from all processes is 100,000. So this is where I got from the MPI reduce command. Okay. The value of A, the total value of A is kept in this variable. Look at the MPI printf. Note. So you can see note. So note 1 A equal to 25,000 and note 0 A equal to 20. Okay, note 0 A equal to 25,000. Okay, because we already divide it. Total from all processes is sum. Okay, where is the sum? This is. Okay, so this sum, I call this sum to get total from all processes. So the value of sum is actually keeping whatever the value A from all other processes. So the value A from all other processes is 25,000, right? So this variable will keep 25,000 plus 25,000 plus from 4 all other processes. That's why total processes is 100,000. So it only can appear at node 0 because node 0 is the destination. Only note 0 hold that 100,000. The rest, it does not hold the value of sum. This is what we call as MPI reduce. Okay. Okay ke? So I look at you guys dah macam bening je. So which part yang you all bening? So atau you're fine? Okay, we actually, that's all actually. Okay. And then if you notice, I did put one example of matrix multiplication. I don't really plan to explain each time, but I'm thinking if you would like me to explain, this is matrix multiplication. Okay, there are few examples on how to distribute the load for matrix. Okay, so this matrix using 3 array A, B, and C, where we keep the results, we keep the answer, and the size of matrix is 8. So 8 times 8. Okay. So if you notice, this function is to fill up the matrix, and this function is to print the matrix. So nothing related with MPI. Okay. Then this, you can notice that we are trying to get the my rank and the size using my rank and P as variable. Okay. And this code is only to control the size is divided by P. It's not if it's not 0, so it's not divisible. So it's just like a message if we request numbers like more than 8. Okay. Because our size is 8 and our P probably 2, 4, and 8. So we cannot request more than 8 actually if you are referring to this code. Because the size is 8, the size of array is 8, P is the total number of processes. Okay? So if the size is 8, 8 divided by 8 is 0, right? So this one will be not true. Okay? But if you are using more than 8, 8 divided by 10, so it already true for this one. So you will see the message matrix size not divisible by number of processes. You only can request 2, 4, and 8 for this program. Okay. So this is how they try to divide the row to processes that you request using from my rank times size divided by P to my rank plus 1 times size divided by P. Okay, for example, okay, right now we have so our size is 8. Our size is 8. Okay. So right now our P is 4. So P is number total processes, yeah. Remember? Okay. So our rank will be 0, 1, 2, and 3. So I think everybody are mathematician, you may be better than me. You can calculate what is the value for from. So let's see. Now my rank is 0. My rank is 0. Okay. The from will be what is from? My rank is 0 times size 8 divided by 4, right? 8 divided by 4 is 2, so since our rank is 0, so from will be 0. And 2 will be 2, right? My rank 0 plus 1 is 1. 1 times 2 is 2, right? So this is if my rank is 0. So now we request for 4. So if my rank is 1, from will be 3, 2 will be 5. Okay. Now if my rank is 2, from will be 6, 2 will be 7.
8.
Okay, my rank 1 times 2. Oh no, this one is 2. Sorry. 2 and this one is 4, right? This one is 4. This one is 6. So, and then if my rank 3, this one is 6. This one is 8, right? Okay, so please keep in your mind. We have 4 processes. Our rank is 0, 1, 2, 3. So you can do 0 to 2 for 0, 2 to 4 for 6, 6 to 8. And then how they are using this value to distribute the load. Okay. So they are using NPI broadcast scatter to distribute the value of B, the array B, and then distribute the value of array A to all other processes using A from then C, size by size divided by P. Okay. And this is actually, this code actually will divide the number of row in that array each processes. Okay, I think everybody know if you are using the matrix multiplication, you need to have interloop, right? Okay. So the first one is actually to move from one row to another row. From I equal to from I smaller than 2I plus plus. So if my rank 0, I equal to 0, I smaller than 2. Right? Remember, my rank 0, from will be 0, 2 will be 2. So it will start with I equal to 0 until I smaller than 2. So it will go for row 0 and then row 1. Then it will execute the loop. So this for is to move from one row to another row. And then this for is to move from one column to another column. So let's see if you have something like this in your array. Okay. So it will the first loop will move from 0, 1, 2, 3, 4, 5, 6, 7. So it will move from here to here. Okay, that is the first loop. So the next loop, it will move from here to here to here until the end of size. So your size is 8, right? For j equal to 0, so it loop until 8. Remember our value start from 0, so 0, 1, 2, 3 until 7. So the next loop, we allocate the value for the array C. Array C where it is the answer. Okay, you can see, I think I'm not so sure whether you got directly you have that matrix.
Ada.
Yeah.
Saya nak masukkan. Alex, you see matrix works here. Everybody list your directory.
Yes.
You have, right? Matrix works. Salah itu nak. Betul tak matrix?
Oh.
Ini matrix. Matrix where X. X. Ini X. Control L. You want to clear your screen, you just Control L. Okay. Function main warning I don't know find C. Okay, yes.
Oh, that's okay. Error tu warning je kan? Just warning is okay. The system can execute. Keluar tak dia punya executable file tu? Warning hijau. Dia kan? So just run. The warning is okay. So So NPI run, so this one I use 4.
Boleh? Boleh.
Then, so if you already run the code, you can see that computing slice 0. 0 is actually referring to process 0 from row 0 to 1. Okay? Because we have 8 rows. Because our size is 8 times 8, right? So we have 8 rows. So when we request 4, each processor will get 2 rows each. Okay? So computing slice was processor 0, it will start from row 0 to row 1. Slice 2 from 4 to 5. 1 from 2 to 3. Okay, you can see that 0 to 1 and then 1, 2 to 3 and then 2, 4 to 5 because each processor will have 2 rows each. So if you are using 8 processors, each processor will have 1 row. So that's why we can request more than 8. Okay? So this is an example if you, and then there is one more example where this matrix multiplication, they are using the one that I showed you just now. X, the value of loop divide by size. Okay, so this actually depends on you. What kind of technique you prefer. So when you need to distribute the data, you can start calling NPI recast, scan, or so there are many NPI. So that's why I want to explain a lot because I prefer you really understood what you have understand right now rather than we learn a lot but you don't really understand everything because it's already mixed up. Okay? So you can refer to this code if you have your own matrix multiplication. You can Google actually. You can Google matrix multiplication in OpenMPI and there are so many samples. Okay. So I guess I have 15 minutes more, right?
10 minutes.
15.
10.
10. Okay. So I have 10 minutes more to wrap up whatever we have learned today. So what do you think? Do you have some clue right now to start your parallel program? So remember, the most important thing what you learned for today referring to distributed memory architecture. So that's why you need to understand how to passing the message. Okay? For parallel programming model referring to distributed memory architecture, there are few. The most common is OpenMPI and NPI-SPH. Okay? So they have a routine that you can transfer, you can exchange the message. So this afternoon we start with the first program where you learn how to get the size and rank and display. And then you understand that all processors will see the same program simultaneously. So that's why you can see how the printf. Okay? But remember for scan, only the root processor can do that, not all. But to display, all processors can display, so they will see the same program. Okay, and next, when we do the ping pong, you start and see that how we can control. Because remember, when all processors will see the same program, but we don't want that all processors do portions of this program. So you start using the if and else. When you are using if and else, we are using the myRank to control who can see this statement, who cannot see this statement, then you can start exchange the data using NPI send and NPI receive. Right? Okay. Then the third one is greetings, where you just do the ping and not for. And then the fourth one, I teach you how to distribute the load. Okay, using the X equal to 100 million divided by size. But we don't really do any communication in that example. And then next, I show you how to use the NPI decast. The NPI decast where you distribute one processor distribute to the other processors. And then next, the same example, I show you how you can use the NPI reduce where you gather all the data from all other processors and you sum it up and put in processor 0. Okay. So the most important thing, if you can look at the sample example, there are only few lines for MPI code. The rest is actually how your creativity to factor the my rank that you already labeled, and then how you're going to distribute the data if it's needed. If doesn't need it, you don't have to call any routine, send, receive, broadcast, gather. Okay. So I hope by now what you need to understand is again the concept of MPI form, size, rank. You have to include MPI.k to get the value of size and rank. When to use the communication, either you need to use the communication or you don't need to use the communication. Okay, and the difference between point-to-point and collective, and how to distribute the load. But today I don't have much time to teach you how to distribute the load inside an array. This is the example actually that just now what we learned in matrix. How you distribute inside an array where you use a number of row, right? 0 to 1, and then 2 to 3, 3 to 4, 0 to 1 for processor 1. That is how we distribute inside the array. I show you many examples before how we distribute the load using a loop, not an array. So array, I just show you one example, which is inside the matrix. Okay. Okay. So any question? So I hope you understand. Okay. Okay. Thank you. Assalamualaikum.
Okay, on the 10th of September, okay, we are organizing introduction to HPC workshop. Okay, so it's only 50 ringgit. Okay, and it's targeted for undergraduate students, but postgraduates, if you still want to join, you can join. It will be a one-day workshop, right?
Asila Wati for the workshop. And now I would like to invite Dr. Zanaria Abdul to give our speaker a hand of appreciation.
Hey. And then
we are going to have our closing at the seminar room, so we hope all the participants will
student sini lah. Student sini boleh kena dari universiti. Siapa tu?